Hi everyone, welcome back. So in this video, we're going to discuss constitutional isomers. And what we're going to do is, instead of just defining what constitutional isomers are, I'm going to slowly derive some molecules, and we will build upon our knowledge of Lewis structures to get there. And then we'll define what constitutional isomers are. So what we'll do is we'll just basically start off by trying to draw some Lewis structures. So let's draw Lewis structure for the molecular formula here. So let's say we have a molecular formula of C2H, sorry, not C2, we have C3H6. Okay, that's a molecular formula we have, and we want to build a Lewis structure for this molecular formula. So let's start by counting the number of valence electrons. So number of valence electrons. We have 3 carbon atoms. So 3 times 4, valency of carbon is 4. So 3 times 4 is 12 plus 6. We have 18. So we have 18 electrons total. Okay. So carbon again, quick review, is 4. Hydrogen is just 1. So 4 times 3 is 12 plus 6 is 18 electrons. So this is a 18 electron system. And we're going to develop some Lewis structures for this. Now, again, going back to what we already know, hydrogen can only be on the periphery. It only forms 1 bond. Carbon is tetravalent. It would like to form 4 bonds. Since there are 3 carbons here and the only other element here is hydrogen, it is very likely that the 3 carbons are bonded to each other. And again, it's just a guess that I'm taking. But whenever you have a situation like this, it is very likely that the other elements are all bonded to each other, because hydrogen cannot be in the middle. It cannot be between 2 elements. And so let's just start off by drawing 3 carbon atoms, and we'll say these are all bonded to each other. Okay. Now, once we're done with this, that leaves us with 3 bonds on this carbon at the end, 3 bonds on the other carbon here, and 2 bonds to the carbon in the middle. And then once we've done that, that basically all the bonds that carbon would like to make. This carbon is making 4 bonds, that carbon's making 4 bonds, this carbon is also making 4 bonds. Okay. Now, if we look at the number of hydrogens we have 6 hydrogens. So let's go ahead and put those into our structure. So one possibility for those hydrogens is, let's go ahead and add 3 hydrogens on this carbon. So that kind of makes this carbon complete. We're left with 3 more hydrogens. So we could add 2 hydrogens here. Okay. And that's 3 plus 2, 5. So that leaves us with just 1 hydrogen for that other carbon. And then what you notice is we're left with no hydrogens, and this carbon still has 2 open bonds. There are 2 valencies that it has to complete. And we cannot include a charge here because overall there's no charge on this molecule. So that means this structure that I came up with is not the correct representation for this molecule. So let's go ahead and rearrange it. Okay. And what I'm going to do is I'm going to take one of these hydrogens from the middle carbon here and include it. Or what we can do is we can take both hydrogens from this middle carbon and then put those on this carbon, the other carbon at the end. So that would give us 6 hydrogens, but then we have a carbon with 2 open valencies, okay, and there's nothing that we can do here. So even that's not right. So let's go ahead, take one of these hydrogens and then move that to the carbon in the middle. So now we've put 6 hydrogens among the 3 carbon atoms, and there are 2 carbons which have open valencies on them. And what we can do in a situation like this is, because this carbon needs one more bond, that carbon also needs another bond, what we can do is we can actually include a double bond between them. So that gives us a Lewis structure now, where every atom should have an octet around it, and plus it should also satisfy the total number of valence electrons. So let's make sure that that's true. If you look at this carbon, it has 4 bonds to it, octet is complete. If you look at this carbon, there are 1, 2, 3, 4 bonds to it, so octet is complete. The other carbon here has 1, 2, 3, 4 bonds to it, so octet is complete. So every carbon here has a complete octet. Now I'm not even counting the hydrogens, because what I can see is visually every hydrogen has only 1 bond. That means its octet is complete. So every atom has a complete octet in this structure. Now let's make sure that the number of valence electrons also matches the total number that we had here. So if you count, you have 2, 4, 6, 8, 10, 12 for one bond, 14 for the other bond, because this is a double bond. So every bond is 2 electrons. So we're at 14, 16, and 18. So that's total number of electrons. So that structure has 18 electrons. Now, is there another possibility for these carbons to be bonded to each other, or for this molecule to be formed? Let's try something else. I had initially put the 3 carbons in a straight line, like a chain. What if, actually, even before we go there, let me draw another structure. What about this structure, where we have double bond here, and then carbon, hydrogen, 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 and hydrogen. Now what I've done in this structure is I've drawn something that's very similar to the top structure, but I've relocated this double bond between the first and the second carbon. And in this particular case, we could say it was between the second carbon and the third carbon, or the middle carbon and the carbon to its right. And the second structure, we have the double bond between the middle carbon and the carbon to its left. Are these different structures? The answer is no. How do we know this? Because if I take this molecule and if I just flip it over, do a 180-degree flip on it, would horizontally flip this molecule, I'm going to get that same molecule. And so because of that, they are identical. They are the same molecules. Okay. Now the other way to think about it is to just look at connectivity overall. What we have is a carbon that's bonded to 3 hydrogens and another carbon. Carbon bonded to 3 hydrogens and another carbon. This carbon is double bonded to another carbon and a hydrogen. This carbon is double bonded to another carbon and a hydrogen. And then the final carbon is double bonded to the previous carbon and then 2 hydrogens. And that's what we have here. So overall, the connectivity of every atom is the same, although it is like sort of a mirror image of that, okay? Or it's like a flipped version, but the overall connectivity is the same. So that means these are identical structures. These are the same. They are not different Lewis structures. They are the same. So whether you draw this or you draw that, you've drawn the same structure. Okay. So the other possibility that I want to bring here is a case where the 3 carbons are connected to each other in a ring. Okay. And now that would leave 2 valencies open on that carbon, 2 on this carbon, and 2 on this carbon. Okay. Each carbon has 4 bonds around it overall. And we see there are 6 hydrogens. So what we can do is we can add a hydrogen to each of these open bonds. And we've got C3H6. There's no charge on this because each carbon is making 4 bonds. So what we've gotten here is a different Lewis structure now. This Lewis structure is clearly different from this one or that one, which are identical. okay? So these two structures, whether it's this one or that one or this one, you know, so comparing these two, these are constitutional isomers of each other. What is the relationship between them? Is there something common to both of these structures? Yes, they have the same molecular formula. So constitutional isomers, they have the same molecular formula, which basically means they are comprised of the same atoms and the same number of each kind of atom, okay? So the same molecular formula, but different structure or connectivity. The connectivity is what's important here. So they have a different structure and they have different connectivity, okay? That's what's important here. So such molecules are called constitutional isomers of each other. So what we can see clearly is there are only single bonds between the carbons, between all the carbons here, and there's obviously no double bond to a hydrogen, but there's only single bonds between the carbons. But in this structure, there's a double bond between one pair of atoms. Okay, so they have a different structure. So that's an example of a constitutional isomer. So sometimes for a given molecular formula, you're able to draw more than one valid Lewis structure that differs in the structure or the connectivity. And such structures are called constitutional isomers. Let's do another example of this, a slightly different one, so that we can see the different constitutional isomers that are possible. So let's do one which is C2H6O. C2H6O. Okay, another molecule. So we'll draw the total number of valence electrons. Here, carbon is 4, hydrogen is 1, oxygen is 6. Okay, so it's basically the group number, the total number of valence electrons. So hydrogen is 1. So 4 times 2, 8, plus 6 plus 6. So 8 plus 6, 14, plus 6, 20. So we have a total of 20 electrons in this molecular formula. Again, no charge here, okay? I'm trying to keep things simple here, so I've chosen molecules without any charge. So in this particular structure, again, we have carbon and oxygen and then some hydrogens. So the carbons and the oxygens, they should be connected to each other. So let's go ahead and draw one structure where the two carbons are connected to each other, and then we have the oxygen in the end. And now this carbon here has 3 open valencies. The carbon in the middle has 2 open valencies. Oxygen, remember, makes 2 bonds when it has no charge, and it would have 2 lone pairs. So we'll just draw the bonds for now. So it has 1 open valency over here, and total we have 6 hydrogens. So we can put those hydrogens here, because we have a total of 6 open bonds. So that takes up all the 6 hydrogens. Now oxygen, when it is bonded to 2, when it has 2 bonds to it, no charge, it should also have 2 lone pairs. So this is one Lewis structure, and we can confirm that, I would say you should go ahead and confirm that every atom has a complete octet, and the number of electrons will count. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we have a total of 20 electrons here. Okay. Now, when we initially drew it, we drew 2 carbons connected to each other and then the oxygen, but it does not have to be that way. I guess we can also draw the chain like this, where we have the oxygen in between the two carbon atoms. And so now the carbons both have 3 open bonds. Oxygen has 2 bonds to it, no charge, so it should have 2 lone pairs to it. Okay, so now for this carbon, 3 open bonds, which can be filled with 3 hydrogens from the total of 6. And the other carbon has 3 open bonds, so the other 3 hydrogens go over there. So now what we've got is another Lewis structure. And if you count the total number of electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So 20 electrons. So that means these are 2 Lewis structures which have the same molecular formula again, okay? So these are both now going to be constitutional isomers of each other, because as you can see, the connectivity here or the structure is clearly different. We had the 2 carbons connected to each other and then the oxygen. Here the oxygen is in between the 2 carbon atoms, so there's a difference in connectivity. So this would be another example of constitutional isomers. And so what I would suggest is you should practice drawing out constitutional isomers for a given molecular formula, but you should be able to do it the other way around as well. If you're given 2 molecules, you should be able to predict if they are constitutional isomers of each other. So let's go ahead, try that out, okay? Let's do an example where we're going to predict if a given set of structures are constitutional isomers of each other, okay? So are these structures constitutional isomers? That's the question that we're trying to answer here. So let's say we have a structure, we have carbon, carbon, nitrogen, and we have carbon, and we have another structure, let's say we have 2 structures, and what we want to find out is, are these constitutional isomers of each other? So what we can do is we can go ahead and calculate the molecular formula. Let's see if the number of atoms and the total number of atoms and the atoms of each kind are the same. So for this particular one, I'm going to say this is a C3N, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9. H9. So this is C3NH9. This one here is 1, 2, 3, C3, 1 nitrogen, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. So it looks like they're both the same molecular formula. And then the other important thing is, do they have the same connectivity or a different connectivity? So if you look at it, the structure, the 2 carbons or the 3 carbons are connected to in a chain, and then one of the end carbons is connected to the nitrogen, and then we have hydrogens around them. Whereas in this structure, we have 1 nitrogen which is connected to 3 different carbon atoms. Okay, so very different from what we have here. So that means we have 2 structures which have the same molecular formula, but they have different connectivity. And so that means these are constitutional isomers of each other. Okay, so we basically worked through these structures, and we've proved that these are constitutional isomers of each other because they have the same molecular formula but different connectivity. They are constitutional isomers. I hope this is helpful. So practice a few more examples, and hopefully this should help you through. Bye.